And we'll go ahead and get cracking into, we've got 3 sections. They are 1.6, 1.7, 1.8. We're going to be talking about measuring matter and like making proper measurements of things. And we're also going to be talking about density today. So we talked a little bit about density yesterday because density is a physical property. But let's go ahead and let's these. Nope, not right now. Okay. So we have our quiz that's up. That will be due today at 2 p.m. I had a question before class of if that's going to be, it's an open resources. So you can look at it and you are going to, the way that Proctorio works is it watches your face. And if you're never on there, then it's going to flag your test or quiz and it's going to notify me. It's like something suspicious was going on this camera. I'm not going to look at this time. However, during exams, in the event that there's something suspicious, like if I see 2 people there or something, and then one person whispering into your ear or something like that, well, that's going to be, we're going to have a conversation. But for this one, I'm really more interested and concerned with making sure that you've worked out all the kinks with respect to Proctorio. So here we've got 2 images, well, technically 4. We've got a piece of a Hershey's bar and, well, a melted piece of a Hershey's bar. And then we've got an Oreo, we've got a broken up Oreo. Classifying these with respect to changes, physical or chemical changes. These, how would you classify those? Let's go with right hand if it's a chemical change, and then both hands for the roller coaster of excitement if it's a physical change. On 3, 1, 2, 3. Woo! That's right. The roller coaster of excitement is going to answer that this is indeed a physical change because it's still an Oreo. It's still a piece of chocolate. Sure, it's different. It occupies a different space, but for all intents and purposes, it's a physical change. Now, next up, we're going to be talking about measurements today. And the measurements that we're going to talk about are related to a couple of different quantities. Now, these are just major quantities that we need to be familiar with. Length, mass, volume, tide, temperature, and amount of a substance. For the units here, these are what are known as SI units. So SI stands for System International, the international like standards system, and these are all related to the measurement system. So meters, well, you measure something, a table is 2 meters, or a table is 1.5 meters. The mass of something, we measure that in grams. Volume, we're going to measure that a couple of different ways. We'll measure it in liters, but you might also see a liter or a cubic meter or other units related to those. So a centiliter or a milliliter or a cubic centimeter, for example. We talked about that a little bit yesterday. Our basic unit for time is going to be in seconds. Basic unit for temperature. This is a little bit funky because I'm sure that everyone's familiar with degrees Celsius and has a sense of, or hopefully has a sense of where that is. Does anyone know what the melting point of water is in degrees Celsius? It's boiling. 0, exactly. So the melting point or the freezing point of water is going to be 0 degrees Celsius, which by the system that we use in the United States, that's 32 degrees Fahrenheit. The other measurement, the measurement that's more commonly used in science, is one known as Kelvin. Now, I think it's a very fair question to ask why. Well, one example is if you go to, let's say, if you go to Finland and you decide that you want to spend the month of December in Finland, do you think it's going to be cold? Yeah. because it's a month of the year in Finland. I always think of Finland as basically a very cold place. Now, when you're there, there's going to be snow on the ground, everything's going to be frozen. Is it going to be exactly 0 degrees Celsius there? Or would it possibly be lower than that? -15 or something like that? Absolutely. Measurements or temperature measurements in Celsius are somewhat similar to degrees Fahrenheit because they can be negative. It can be -10 degrees Celsius. It can be -35 degrees Fahrenheit. So it is possible for something to have a temperature as low as or as less than 0 degrees Celsius. So you could have a negative temperature in degrees Celsius. Kelvin, by comparison, is what's known as an absolute measurement system. The lowest temperature, the lowest feasible temperature is 0 Kelvin, which I want to use that terminology and make sure that you're familiar with that. When you're describing the temperature of something in Kelvin, you say it is 0 Kelvin, 15 Kelvin, as opposed to 15 degrees Kelvin. Notice the not symbol, that little circle, that's NaUGHT, not, that's not present for Kelvin. So when you're describing the temperature Kelvin, you'd say it's 25 Kelvin. Now, we're going to get into the conversion from degrees Celsius to Kelvin in just a moment, but the standards that are used typically in most scientific fields are either going to be degrees Celsius or Kelvin. The amount of a substance is typically going to be measured in mole or moles. Has anyone taken a chemistry class before and has talked about moles? Okay, now I'm going to say the thing that every single person who ever teaches or takes a chemistry class says about moles. They say, it's really not that complicated. And you think, oh, okay, cool. I know things that aren't complicated. And then they say, it's just like a dozen. And then you say, cool, I know what a dozen is. And then that's like your first 2 steps into the discussion of moles. You're like, I got this. And then they throw a number at you. The number representing moles is 6.02 times 10 to the 23rd. And I personally, the first time I heard that, said, you know what? The first 2 steps, I was with you. But now you've thrown this number that is 6.02 times 10 to the 23rd, and I think, I'm no longer with you. Now, that's something that I want to work, that we're going to be talking about today a little bit in depth. And I want to make sure that everyone feels comfortable with that. And in the event that you struggle with the concept of a mole, you're not the first person, you're not going to be the last person. I remember whenever I first took a chemistry class, I had lots of friends who were like, oh yeah, it's easy, I got that. And then I remember sitting there being like, I don't think that it's easy. I believe that it's possible to learn, but right now I'm struggling with that. Now, here is that number. One mole of E is 602.000.000.000.000.000.000.000 of anything. So what's helpful for me is to have a couple of kind of simple relationships. If I tell you that, okay, so let's use the relationship between a dozen and a mole. If I tell you, hey, go buy a dozen eggs, how many eggs have you purchased? 12. Okay, that's like the first lesson. That's where everyone's like, okay, cool, I'm with you. And now if I say you have 3 eggs, is that exactly a dozen, less than a dozen, or more than a dozen? 3 eggs is less than a dozen. Is everyone with me there? Okay. Now, if I tell you, congratulations, you won the lottery, and the lottery this week was 1 mole of dollar bills. Are you mildly interested, over the moon because you have more money than any person has ever had in the history of time. Or yeah, those are our two options. Are you like, yeah, I got a mole of dollar bills? Or are you like, gosh, I can buy 4 Amazons and 1 Apple, and I can just have that much money? Where do you think you are? I'm getting a nod of like, yeah, I'm in that Amazon Apple. You're absolutely right. Because if you have 1 mole of dollar bills, this is how many dollar bills you have. And that's one of the things that I think is really helpful to think about. Put it in something that's like kind of relatable. Not relatable, that's the wrong word, because nobody has a mole of dollars. But put it in something that's kind of tangible and that you care about, or that you're interested in. Because whenever I tell you, hey, 12 grams of carbon is that many atoms of carbon, well, those are a couple of things that are kind of difficult to wrap your mind around. Because what does 12 grams of carbon look like? I don't know. Can you put it in your hand? Maybe. I don't know. It's tough to wrap your, like, these are things, whenever we're talking about a mole of a substance, it's really difficult for it to be tangible. So I always like to use the exercise of, well, not necessarily how does that make me feel, but how am I responding to a mole of something? Versus, is this, when you're given a number, is that less than 1 mole, exactly 1 mole, or more than 1? Does that make sense? So when you can make it something that is like, that you would care about, then I think that it's easier to process this sort of information. Now, this number right here, writing that number out. I think if I close this slide and said, hey, write the number for a mole, most everyone would get to 602. And then after that, they just start writing zeros, and then they look at their paper and they'd be like, I think that's enough. Well, that's why we don't really want to have to write all those zeros. So what we can do is use something known as scientific notation. So we can translate or convert this number, rather than having all of those zeros, have a notation that is times 10 raised to a certain power. We can alternatively use metric prefixes. Now, metric prefixes are things that you're probably familiar with. For instance, this right here. This bottle is 547 milliliters. Milli indicating that it's less than 1 base unit of liters. Does that make sense? So these are things, these metric notations, you're probably a little bit more familiar with them than you might think just based on that. Now, this number right here, 8675309. Whose phone number is that? That's right, Jenny's. 8675309. It's a song. That's a dated reference then, because you know what? It was a dated reference when I was in high school and when I was in college, but here we are. We can rewrite that number using scientific notation. The convention that you use for writing a number in scientific notation is to have the leading number followed by a decimal place, and then any other non-zero digits that are not trailing. Any other non-zero digits until you reach a point where there's a trailing zero. So now, an example of that would be something like, or another example, I'm sorry, would be something like 15050. Okay, so that's 150,500. If we wanted to write that in scientific notation, think about scientific notation as a means to be efficient, as a way to write as few numbers as possible. what we would do is we would take our first or our leading number. What's our leading number? The 1. Then we're going to write all of our non-zero digits or any zeros until we get to the trailing zeros. So what we're going to do here is we're going to write 1 point, then 505. I'm not writing these last 2 zeros because they're not significant. Now, the next thing that we're going to do, does anyone want to take a guess, looking at 8675309, and guess what I need to do for the times 10 to the 1 power? Move the decimal place. Okay. Well, what I need to do is I'm going to write 1.505 times 10 to the, how do I get this equal to this right here? To the what? To the 5th power. You're absolutely right. Okay, now it gets a little bit complicated and tricky. Whenever I write this number, 150,500, basically, I have a decimal that I have not put at the right of this second zero. Can everyone kind of visualize that? Because I told you the number was 150,500. Okay. Now, if I want this other number, this 1.505 times 10 to the 5th to mean the same thing, effectively what I'm doing is I'm moving my decimal place from, do it on the screen, from right here, I'm moving it 1, 2, 3, 4, 5 places. Does that make sense? So now let's take a look at these other numbers. Which one of them is going to be the largest? We have 240, we've got 24,000. We also have 2.4 times 10 to the 3rd. And then we have 2.4 times 10 to the negative 3rd. Now we have looked at just a positive exponent. If you take this 1.505 times 10 to the 5th, which direction are you moving the decimal place to write the complete number? Are you moving it to the right or are you moving it to the left? You're moving it this way, to the right. Whenever you have a number with scientific notation, I personally always take that number and I say, I am translating that to the complete number. So I'm moving it to the right 5 places, and then I'm going to write 150,500. So then, if we wrote option A, we're moving the decimal place 3 times. So what are we going to end up with? 2,400. Okay. So now, based on a positive exponent, what do you think you do with a negative exponent? Which direction do you move that in order to convert to the full number? You move it to the left. So now what we have is, well, let's see, be moving it 1, 2, 3. So effectively we've got 0.0024. Does everyone follow that? Okay. So then we've got 24,240, 2,400, and 0.0024. If you want to, if you think that the correct answer is C, ride the roller coaster of excitement. 1, 2, 3. Yeah, we worked on that. Okay, so a negative exponent, you're moving it to the left. A positive exponent, you're moving the decimal place to the right. Now, this gets a little bit tricky whenever you're converting back and forth. What I personally do is whenever I see a positive exponent or a number written in scientific notation, I'll use scratch paper and I'm going to immediately translate that to the whole number or to the number in non-scientific notation. because it makes me easy, or it makes it easier for me to visualize the magnitude of that number. Okay, how's everyone feel about this so far? Okay, great. Now, when we take a number like 0.0000123, we write that in scientific notation. This is where it gets a little bit complicated, because we're taking this number that is smaller than 1 and we're moving our decimal to the right. We're converting that to scientific notation. We're giving it a negative exponent. Think about it as, if I'm given the whole number and I move my decimal to the right, it's going to be a negative exponent. If I'm given the exponent and it's a positive exponent, then I'm moving my decimal place to the right. So you have to, whenever you see these sorts of problems, think about, well, what number am I provided with? Am I provided with the number written in scientific notation, or the whole number with all of the values? When you're given the number with all of the values defined, then you look at, or you move it to write it in scientific notation for its first non-zero digit, followed by the next number, and you move your decimal place, in this case, 5 spots to the right, so it's a negative exponent. Now, which of these numbers is going to be the smallest? Okay. What do we know about answer option A? We're given a number in scientific notation. So where are we moving the decimal? Or which direction are we moving the decimal? To the right. Okay. Our next number, answer option B, 0.024. Well, it is, let's go ahead and write out A is 2400, because I've moved it 1, 2, 3, so 0, 0, so 2400. Does everyone follow how I converted that 2.4 times 10 to the third to 2400? Okay. And there's nothing really, I mean, whenever I have a problem like this, I will write out just on my scratch paper or worksheet or whatever. I'm just going to write that out. So I'm going to fill in the, I will do these little cloud type of movements to show where I'm moving my decimal place. So I've moved it 1, 2, 3 spots. So that's how I get 2400. Is A larger or smaller than B? It's larger. So we can go ahead and dismiss A as an answer option as the smallest number. Is C larger or smaller than B? It's smaller, so B is out. And now we've got 2.4 times 10 to the negative third. We're given our value in scientific notation. So which direction do we move our decimal? To the right or to the left? To the left, because it's a negative value. So here we've got 0. And I like to write that leading 0 and then put my decimal, and then I'll say 1, 2, 3. So 0, 0. 0.0024. So which number is small, C or D? C. Okay, cool. Is everyone good with that? Okay. The question that you really, whenever you see those sorts of problems, is ask yourself, well, am I given the number in scientific notation, or am I given the number in complete notation with every value defined? Now we have our prefixes. Kilo, milli, nano. The ones that you're probably most familiar with are kilo and milli, because if you go to the grocery store and you buy some aspirin, you're going to probably buy aspirin that's 250 milligrams. So I always like to try to translate it into something tangible. So if I buy 250 milligrams of aspirin, that's small enough that it's going to fit in the palm of my hand, and I'm not going to be like, oh, this is really heavy. It's going to fit in the palm of my hand, and that's all there is to that. Kilo, on the other hand, well, has anyone ever heard the term kilo or a kilogram? Most people say, oh yeah, Breaking Bad, or any other movie with drugs, because generally it's like, oh, a kilogram of cocaine in a movie or something like that. Now, whatever somebody in movies or TV shows where someone's like, yeah, we've got 15 kilos. Is that handed over to someone in the palm of their hand? No, it's like they open the trunk of their car and there it is, whatever substance. I think that it's helpful to put these things in terms of like making them tangible. So a milligram fits in the palm of your hand. A kilogram, well, that's like a brick size. Our notation for a kilogram is 10 to the third, or our notation for a kilo of something is 10 to the third. A milli is times 10 to the minus third, and a nano is times 10 to the minus 9. So here what we have are different quantities. Which one of them is the smallest? Okay, they are all 2.4. We've got 2.4 grams. A gram is our base unit of mass. 2.4 kilograms. If we wanted to write 2.4 kilograms and convert it to grams, we would say 2.4 times 10 to the third. So that would be effectively moving our decimal place 1, 2, 3. So that's the same as 2,400 grams. Does everyone follow that? Then milligrams, we would say 2.4 milligrams is 2.4 times 10 to the minus third. So we move our decimal place there to get to grams. I'm converting all of these to our base unit of grams. 2.4 nanograms. Well, that's moving the decimal place times 10 to the minus 9. So 9 times to the left. Does everyone follow that? So where are we with the smallest quantity of these different options? Is it 2.4 grams, kilograms, milligrams, or nanograms? Nanograms, absolutely right. Now, if 250 milligrams fits in the palm of your hand, you can see that little pill or capsule or whatever. What do you think of 2.4 nanograms or 250 nanograms for that matter? What do you think that's going to look like? Well, it's going to fit in the palm of your hand. Do you think that you're going to be able to see it? Probably not. If you can, it's very, very, very faint. Absolutely. That's a great question because all of these are prefixes. Some of these prefixes are a little bit, we use them in different contexts. For instance, if you look up here, tera and giga, has anyone ever used those prefixes for something? What? Absolutely. A terabyte. Well, computers are kind of tricky because they deal with a byte system, so they're bits and bytes, so it's base 8, but which is a great controversy if you really want to get into angry arguments on the internet. But could you have a teragram of something? Absolutely. Because at the end of the day, tera and giga are prefixes for times 10 to the 9 or times 10 to the 12. So you could get, I'd like 1 teragram of I'll just go with gold. Yeah, there we go. So you could get that quantity. Tera and giga, actually, mega, giga, and tera, they're not super commonly used in lots of research. Are they still relevant? Absolutely. These are still quantities that are used in different scientific fields. What I want y'all to know is a range from kilo to micro. In most laboratory settings, that's the range that most people are going to work with. My background's in biochemistry, And everything that I did was a range from kilo to micro. So being able to answer questions like we just did with which is the largest, which is the smallest, and using these prefixes is going to be very helpful. Now, these prefixes all work into them scientific notation, because a kilogram, a kiloliter, that is going to be times 10 to the third. A microliter is times 10 to the minus sixth. The way that I personally try to look at this is I try to convert back to my base unit. So if it's a kilobyte or a gram, kilosecond or something like that, which is another thing that's worth noting. These all have a time scale, or you can all use all of these in terms of a time scale. Because you could say, well, man, I was waiting for my friends to pick me up. I waited an entire megasecond. Whoever you tell that to is going to immediately think like, oh crap, I gotta translate this. Okay, 1 megasecond. That would be, you waited 1 million seconds. Okay, 1 million seconds. 1 million seconds times or divided by 60. Then you're just going to get tired, or that person is just going to get tired and say, just tell me how long you waited. And you're gonna be like, well, I waited a full day. So these are all kind of term relationships. So what I want you to be familiar with is kilo all the way down to micro. Now, where they get a little bit complicated is the capitalization. A gram, it's a lowercase g. A gigagram would be a capital G, lowercase g. Kilogram is lowercase k, followed by a lowercase g. Kelvin is a capital K. Meter is lowercase m, and mega is going to be a capital M. Now, what's the mass of this apple in scientific notation? Well, if it's 172.3, we're going to translate this by removing our decimal place so that we have one numeral, one number, followed by a decimal, followed by all our other non-zero digits. So this would be 1.273 grams, as opposed to 172.3 grams. This is a little bit tricky because 1.273, the units are the same. This is 172.3 grams, which that is the exact same as 1.723 grams. What about converting this to kilograms? Well, 172.3, if we want to convert that to kilograms, it would be 0.1723 kilograms. Volumes. Well, the volume of this liquid in this graduated cylinder is approximately 45 milliliters, which is the same as 0.045 liters. Because these are, so if we jump back for just a second, what's helpful for me personally is to think about, okay, right in here is, let's go with, I use liters, so 1 liter. I think about conversions, and I say 1 liter is equal to, does anyone have like a large water bottle with them? See if this will work. This is 26, this is 769 milliliters. Okay, I'm gonna steal it for just a second. So what we have is, actually, there's a lost and found here. Usually there's stuff that has been lost that I find. I was really kind of hoping for a 1 liter bottle, but if you go to the grocery store, or if you go to the gas station across the street, can you buy a 1 liter Dr. Pepper? Yes, you can. Can you hold that 1 liter Dr. Pepper in your hand? Yes, you can. That 1 liter Dr. Pepper is the same as saying you have bought a 1,000 milliliter Dr. Pepper. Does everyone follow that? So when we look at our milli, well, 0.001 liters is the same as 1 milliliter. Does everyone follow that relationship? What I think is also helpful is to say 1 milliliter is equal to 1,000 microliters. Does that make sense? So we've gone from something that's kind of tangible to then 1/1000th of that thing. That 1/1000th of a liter is 1,000 microliters. So if you have 1 liter, let's just imagine that this bottle that I'm holding up is 1 liter. This is 1,000 milliliters, and each one of those milliliters is equal to 1,000 microliters. So if I held up this 1 liter bottle and said, how many microliters is this? Well, it's 1,000 times 1,000, which would be 1 million microliters. Does that make sense? It gets very, very small and very, very complicated, but I think when you can draw those connections, like times 10 to the third, or times 10 to the sixth, and say 1,000 microliters is equal to 1 milliliter, and 1,000 of those is equal to 1 liter. Then you can make this connection a little bit quicker. Okay. What's the length of this pencil in centimeters? Well, we started at the end, and now we're here. We're at about 17.35 centimeters. And isn't everyone proud of me for not making a reference to pop superstar Drake? Because we started there. Here. Usually I do. Just wait, there will be a time. Because if you don't know, he was on a TV show called Degrassi. Anyone ever see that show? Yeah, it's not very good. Okay. So what's the length of this pencil in centimeters? 17.35. What about inches? Well, it's about, let's see, from 12 over to be about 6.831 inches. What about this pencil in meters? Could you do that? Well, 100 centimeters is equal to 1 meter. So this would be 0.01735 meters. Does that make sense? Or yeah, that's right. Measuring time, 6.5 minutes. Well, 1 minute is equal to 60 seconds. So if we were taking 6.5 minutes and converting it into seconds, it's going to be 60 times 6.5. 60 times 6 is 360, times 0.5 is 30. So we get to 390 seconds. Measuring temperature. Well, like I said, degrees Celsius is what's commonly used. The other one that's commonly used is Kelvin, a measurement in Kelvin. The way that we convert from degrees Celsius to Kelvin is not a super complicated conversion, because all that you do is you take your temperature in degrees Celsius, and to that you add 273. So if something is 25 degrees Celsius, that means its temperature measurement in Kelvin is 298 Kelvin. Now, what is this temperature in Kelvin? Well, if it's 32.7 degrees Celsius, we add to that 273, that gets us 305.7 Kelvin. Now, if I tell you, hey, the temperature outside is 25 Kelvin, is that hot, cold, or Well, let's think about this. If 25 degrees Celsius is 298 Kelvin, then 25 Kelvin is, let's see, 25 Kelvin minus 273. So if it's 25 Kelvin outside, you're going to want to wear a lot of jackets, because that means it's negative 250 degrees Celsius outside. So pretty chilly. So maybe more than a jacket, definitely gloves, and then mittens on top of those gloves, and then mittens on top of those mittens on top of those gloves, and then some sort of spacesuit, because negative 250 degrees Celsius is going to be pretty tough to live in. Does everyone follow that? Okay. So here's our standard temperatures. The scale that we use, our Fahrenheit scale, boiling point is 212 degrees. Our boiling point of water and our freezing point of water are 212 and 32 respectively. The boiling point of water in degrees Celsius is 100 degrees Celsius, which is the same as 373 Kelvin. The freezing point of water is 0 degrees Celsius or 273 Kelvin. Now, absolute zero for Kelvin is, lo and behold, 0. Absolute zero in degrees Celsius is negative 273 degrees Celsius. And absolute zero using the Fahrenheit scale is negative 460 degrees Fahrenheit. I like this figure because it relates all of our different temperatures. It doesn't have the tricky conversion factors, instead it just aligns these things. Can it get higher than 100 degrees Celsius? Absolutely. The sun is hotter than that. This is just all standard, this is all related to water. So that's why we kind of end up there. Now this question up at the top. Can a temperature in kelvins be negative? Nope, that's the exact point and value of Kelvin. There are people who are kind of theoretical chemists and physicists, the people who study like physics at an atomic level. They are, you know, actually reaching absolute zero is something that's kind of an idea. Well, that would be really cool if that was possible, because we have no idea how electrons and atoms are going to behave if the temperature is 0 Kelvin. So that's kind of like a unattainable temperature, but it's something that people try to do. Okay, how does everyone feel about measurements? Okay, great. I would say that the trickiest part about this is being able to make these conversions. What am I given and where do I need to go with it? All right. Next up is density. We talked about density a little bit the other day. We're going to continue that conversation. When we are measuring something, we think about the mass of it and the volume that it occupies. If there was a clone of me that had the exact same body mass, but was a foot shorter and all other dimensions did not change, that person would be considered super dense. Now, typically, whenever you describe someone as being dense, you're basically saying a person's not very sharp, they're not very bright. That's not what we're talking about. Instead, we're just talking about like you're packing a bunch of mass into a small space. We have an equation for density, and that is mass divided by volume. Now, the units for density are going to be grams per milliliter or kilograms per liter. Is density a physical or a chemical property? It's a physical property, you're absolutely right, because that is something that, regardless of, I mean, if you take something that tells you nothing about how it reacts with anything else, it just tells you, here's the amount of mass that's packed into a designated space. Now, liquids. Here, what we have are a number of different liquids. Honey, corn syrup, milk, hand soap, vegetable oil, motor oil. They all separate from one because they have different densities. Now, if you have a lava lamp, like I've ever seen a lava lamp, that operates on one principle of density, but it also operates on a wax, doesn't mix it into water. But my kids have these things that they're like They're plastic and they have a colored solution, like a green solution and then a clear solution. Flip them upside down and all these little bubbles kind of go up. And those are operating on the principle of density. The colored solution is an alcohol and it's like red or blue or green or something like that. And then the rest of it is clear. So they stay separate from one another. That density, that less dense substance is going to float up. The more dense substance, as we see here, the honey, for example, sinks to the bottom. Honey is very dense, it sinks to the bottom. Now, if I put a solid piece of lead in, lead is very dense. It's going to sink to the bottom because it's going to go through all of these, because lead is more dense than honey. If I got a chunk of styrofoam and I threw it in this mixture, where's it going to end up? Just a guess. Probably at the top. Okay, now we measure density to identify a liquid because density is a physical property. The density of water is 1 gram per milliliter. Do you think that the density of, say, let's go ahead and imagine that you went down to the river and you had an ice filter so that there was no like fish or anything there, but you scooped out some water, you filtered it, and then you compared tap water to water from the river, and then you also went down to Galveston and got some of the water from the Gulf, and again, you filtered out any sort of like biotic or biological components, and you compared those three. Let's talk about the composition. The tap water, does tap water have any dissolved minerals in it? Absolutely, especially around here. How do we describe the water that comes from the tap here typically? I'll give you a hint. It's hard. We have lots of hard water here because we have lots of dissolved calcium compared to other places where it's very soft. So if you have tap water, river water, tap water here is probably a little bit filtered, so it's not super hard compared to the tap water. The densities of those are going to be a little bit different. The river water is probably going to be a little bit more dense because it's got some dissolved stuff in it. Now we've got water from the Gulf also. Where do you think that lands on the spectrum of like soft, hard, dense, not dense? What's in the water from the Gulf? I mean, if you're going to be critical and mean like me, then you're going to be like, ooh, a bunch of junk. But if you go and you drink some of the water from the Gulf, you're going to spit it out because there's a lot of what in there? Salt. Salt water versus pure water, tap water, whatever. Salt water is going to be more dense. And so it's going to have a separation, or it's going to separate because it's more dense. Has anyone ever seen, so I think it's, let's see. There's a place in the Gulf, and it's right around where Florida, the boundary of Florida and Alabama are. It's where the water from the Gulf and the Atlantic Ocean meet. Has anyone ever seen pictures of this? The waters are just completely different. They don't mix well with one another. And that has to do with their densities. It also has to do with like the jet stream and currents and everything like that. But it's always a fascinating picture to me because it's like, that's so bizarre how one is like kind of darker than the other one. And one looks a little bit more clear than the other. But one of the major reasons for that is their densities. They're not going to mix because their densities are different. There's lots of other components that make them not mix, but there you go. So you can use density, a physical property, to identify a substance. So this, for instance, like let's say that we got a solution, we put it on a scale, and we determined that the density was 0.79 grams per milliliter. Is that water? No, it's not. If its density is 0.79 grams per milliliter, it cannot be water. Instead, it's got to be something else. If you measured something and the density was exactly 1 gram per milliliter, you got a better chance of it being water. But if it's not 1 gram per milliliter, it can't be water. Does that make sense? Okay. Now here's a example of how you can play around with this sort of thing. Share. There we go. So here what we're going to do is we're going to add water to this. You've got 200 milliliters. And what we can do is drag one of these solids onto the digital balance. I'm going to take this one. 44.8 grams. Now, what we're going to be able to do is we can determine the volume of that. What we can do to determine the volume of something is you could measure the dimensions. Does that piece of metal there look like it's a perfect square or a perfect cube? No, it doesn't. So how easy do you think it's going to be to calculate the dimensions of that? It's a little bit tricky. So if we can't measure the length, width, and height of something, it's going to be tough to calculate the volume of it. Another way that we can calculate the volume of it is by saying, okay, we're going to put it into this water. What is the volume of that metal sander? When we put it in the water went from 200 to 205 milliliters. So what's the volume of that metal? 5 milliliters. So if we have the mass, 44.8 grams, we'll use a calculator. So 44.8 divided by, that's grams per milliliter, we get a density of 8.96. So we could look at that substance and say, all right, well, its density is 8.96 grams per milliliter. Based on a table of known densities, we can determine and identify what that substance is. So that is in your PowerPoint. So you can play around with that tool a little bit. So what we're doing there is measuring the volume of a substance by the amount of water that it displaces. Now, here are 2 pieces of copper. Which one of them is more dense? Spoiler, they're both pure copper. Correct. They're the same because they are both pure copper. The one on the right, well, you can tell that that is where it looks like it's larger than this sheet. And you might think, oh, well, that sheet of copper, you know, if it's thin enough, it might float on the surface of a solution. Well, then you're taking into consideration a number of different properties. You're taking into consideration like the surface tension of the solution. So you're kind of complicating it. But they're both copper, they're going to have the same density. That is because density is what is known as an intensive property. So regardless of if you have 10,000 grams of copper or 1 gram of copper, regardless of the amount, the density is going to be the exact same. Does that make sense? Okay. Measuring density by displacement, that's what we were just talking about a moment ago. So here's another exercise where you can basically play around with that. Determine the mass of something, then the amount of water that it displaces, that gives you your mass, divide by your volume, and you get the density of it. Now, what is the identity of this mystery solid? If our density, so this is going back here, when you determine the density by displacement, so the mass of all of these, the volume of them, you can determine density. And this substance down here with a question mark is going to have a density. So a density, and you've already calculated those densities, so that's what you can do. So this is definitely a good thing to do prior to your quiz. So play around with this tool, okay, because that's going to be on the quiz today. Okay. Measuring density of a metal, the mass. A graduated cylinder filled with water is typically what's going to be used, because we know the density of water is 1 gram per milliliter. Measure the volume that it displaces, and then you can calculate the density of that object. Could you use something other than water? You could, but you're then going to have a slightly different standard that you're comparing to. So you kind of made it a little bit trickier. So it's easier and best to just use water because it has a density of 1 gram per milliliter, because 1 gram of water is going to occupy exactly 1 milliliter. 1 milliliter of water is exactly 1 gram. So there you go. And so here what we have are larger objects. And asking, well, do these objects float, or are they going to sink in these different solutions? So what these things are going to be, these examples are going to be useful for you for your quiz that goes up today. So make sure that you play around with those so that you have a good idea of those. Using density, you can find the mass or the volume of something. So one way, like let's take ethanol, for instance. Ethanol is written typically a shorthand of ETOH. So alcohol, Everclear, for instance, has a density of 0.79 grams per milliliter. If you had 412, let's go with 4.12 liters of ethanol, what's the mass of that? 4.12 liters of ethanol. What is the mass of that? Does anyone have a thought as to what's the first thing that they're going to do to do this sort of calculation? I love it. Convert from liters to milliliters. So 4.12 liters, 1 liter is equal to how many milliliters? 1,000. So 4.12 liters, we can say times 1,000. That's milliliters. So we're talking about 4,102 or 4,120 milliliters. Does that sound right? Okay. Now, if we're looking at all these different equations, we've got density is equal to mass over volume. Then we've got, well, volume is equal to mass over density. We've also got mass is equal to density times volume. Which one of these three, if we're trying to solve for the mass, do you think you want to go for? Because lower left-hand corner. So 4,120 milliliters times 0.79 grams per milliliter. Well, our milliliters are going to cancel out. We're going to be left with grams. So that would be, oh, I have a calculator. 0.79 times 4,120. What did anyone get? 0.79 times 4120. 3254. What are our units here? Grams. 3254.8 grams. Okay, pretty easy to do that, right? Now, if you were to see this sort of thing on an exam, question might be, write your answer or select the answer in kilograms. So if we have 3,254.8 grams, what's that in kilograms? 1,000 grams is equal to 1 kilogram. So 3,000 grams is equal to 3 kilograms. So then we're looking at approximately 3.254 kg. Does that sound right? Does everyone follow how to do that calculation? So being able to manipulate this equation will be very helpful for you all. Understanding if you're given a mass and you're given a density, how do you calculate for your volume? Basically, this is a sort of equation, just do the algebra to rearrange it. That's all that we're showing down here. And if you struggle with that, then just try rewriting it and saying, okay, well, I want to get volume by itself. I can multiply each side by volume, and then I get V times D is equal to M. Okay, well, I want to solve for volume. Then I have V times D divide each side by density, and that's how you get V is equal to M over D. So playing around with that will be very helpful. And that's what I got for today. Is everyone good? Okay. We have a quiz that's due today at 2 p.m. Again, that's like the proctorio component is like getting comfortable with proctorio, making sure that you don't run into technical issues. I know that there might be an issue, like if you're using a tablet or something like that, then it might prompt you like not compatible with an iPad. Then there's going to be a quiz that goes up today that covers all of what we covered today. So questions, expect some density calculations and relationships. Expect this for as many as 2 questions. So being able to manipulate this would be a good thing. Other than that, I'm going to end my recording. I'll post the recording like I did yesterday. And if anything comes up, please let me know. And if you need any help with anything, please let me know. Other than that, I will see you tomorrow at round about, I'll say 9:46 or so. Yeah, you guys can show up at 10 or whatever, but I'll be here. I'm gonna go ahead and say I'll be here about 9:46. Cool? All right.
Could you go back to the same letter different?
Sure, just a second. I'm gonna stop the recording. Have a good one.